So let's move on to our last presentation of the day. We have two presenters here, Ben McNeil and our one and only Quyen. They're going to present predicting and forecasting corporate carbon emissions using machine learning, as usual. Machine learning.
I will go to Ben first, and Ben is presenting first, and I will present later. Yep.
Hello, you guys can hear me, hopefully?
Yeah.
Great. Well, thanks so much for Ivan and everyone for inviting me. I guess wanted to give you a bit of background. It was great actually just hearing that discussion then on carbon emissions data. I am not in finance. My background's actually in climate science. I was 20 years, or still am, adjunct at University of New South Wales. And my background is in understanding carbon budgets and flows and fluxes in the natural world, so oceans and land and the atmosphere. And as a sort of climate scientist, I realized a few years ago that the challenge is obviously activating, not in diagnosing the problem, but solving it. And finance, as you guys all know, finance is where the solutions are. If we can shift the finance curve towards valuing carbon, then we're going a long way towards solving the problem of climate change, and even with we get frustrated with politics once in a while. So I think maybe this project, I guess, Quyen, do you want to put it onto the first slide, maybe? Can you? Oh yeah, great. Yeah. So the first bit is really, I want to give you an introduction for around Emmy. So my background's in climate science, but I've shifted towards in finance. So Emmy is I'm now co-founder of Emmy. What we're trying to do is really empower the financial ecosystem to really value and drive carbon adjusted financials for the world. And to do that, we've come up with, have you got, maybe Quyen, you can, that first slide, yeah, that one. So empowering the ecosystem to really accelerate the transition. And because I've come from the natural world, my background's in data science, and so when I've come into this space, into understanding corporate carbon emissions, it's a very different space, and I realize how hard it is to actually understand what truth is. And going to Lillian's point just before in that prior discussion, the data is, there's many different providers and many different methods of carbon emissions in corporates, and I've come to realize that there's a lot of scatter, and then there's actually a lot of lag too, which I actually I didn't realize that before I came in, whereby the emissions that some companies report are 2 years old. So what we're trying to do with Emmy is really create, maybe if you go forward, Quyen, the next slide, we're trying to understand from the ground up how the carbon risk for any company, and therefore portfolio, as we go up in the food chain in finance, to allow solving the challenge, allow investors, allow the markets to really understand from a quantitative perspective, what's going on. So this little slide here shows you sort of what we're doing, and this project that we're actually collaborating with Nguyen is really key to this. So the center of the ecosystem is this, what we're calling it's the Emmy score, but think of it as a carbon efficiency rating, where instead of just using one metric like revenue, WACI for revenue, like carbon intensity for revenue, which has problems, we've incorporated 12 different financial metrics across a company's financials to benchmark against global carbon budgets for a 1.5, 2 degree and a 4 degree world. And then from those budgets, and then our as well as our own emission estimates, as well as some from providers, which I'll get to later, we can then come up with a really standardized quantitative universal metric, which is a carbon financial metric that allows people to understand where each company lie today. And most importantly, we can actually propagate that into the future based on the IPCC carbon budgets. That's my frame of reference. That's where I come in and bring value to the collaborators we have at Emmy. From this score or this rating, this carbon efficiency rating, we then propagate that through to funds, and then funds of funds to asset owners and up the food chain, for them to really understand and start understanding that the carbon transition is not a binary equation. As you all know, it's not just a black and white. It's not just based on carbon footprinting and excluding coal and things like that. There's a transition, and so this efficiency rating allows investors to really take charge of where the corporates are, and how they can actually adjust their portfolios to be aligned with the 1.5 degree world, for example, but do so without in a growth mindset for their own portfolios. So that's a little bit of how Emmy works. The project we have with Otago is really critical because, as I mentioned before, the left there, we've got the emissions, and they've from scope 1, scope 2, scope 3. The idea is very simple. Can we create a framework to which we can model and estimate carbon emissions just based on financials? So essentially fill in the gaps, but also propagate real-time quarterly reports based on just financials. And so that's the project that we're working on with Otago. It's going really well. And I will leave it up to Quyen to really take through a number of different things we've found on the way. So I'll leave it with you, Quyen, to take through the details.
Thank you, Ben. First of all, I just want to say thank you again for the collaboration. And so today what we are presenting is merely a preliminary result from our past like trial in the past few months. And so like actually we have two results. The first one is in terms of the data reconciliation. Just now, like Leland mentioned, we have so many like different data provider. We have Truecost, we have CDP, but from financial provider perspective, we have like Bloomberg, we have Refinitiv, Aiken, and we also have ISS. Those are like the three big data provider from finance perspective in terms of carbon emission. And so in our first part, what we try to do is that we want to have a clean data set before we actually start model carbon emission. And so like in this process, we start out with the assumption that like, because we are looking at reported emission data, they should be similar, right? Because unlike ESG rating, they do not go through any like transformation process. There is no weighting process at all. We are looking at reporting emission value. They should be the same from 3 different data sources. What is really interesting is that we found that like even for emission data, just raw data only and reported data only, not even looking at estimation, there is a very substantial diversion across the 3 data provider. And then this diversion is substantially prominent in scope 2 and scope 3 emission instead of scope 1 emission. And then if we talk about which one is like more consistent, I have to say that it should be like Refinitiv and Bloomberg, because for ISS data, there seems to be a different approach, especially with scope 3 emission. We try to find like whether it is a systematic difference, whether there is some bias in here. We cannot find any like difference apart from the fact that the smaller firms seem to diverge more in terms of emission value. And then last but not least, when we use emission data, either we use that to calculate the portfolio carbon intensity, that is the raw value, or either we use that to like come up with the low to high emission portfolio, use that for ranking. And so what we find is that even though there is diversion, maybe it will not affect the emission ranking as much as the carbon intensity. So that is our finding. And so like our conclusion is that even with reported emission, there is already diversion. So be really very careful, like what kind of emission data source that you are using. And then also to say that like there's a lot of like different data provider with different modeling approach. And then if we have like different estimation, that is going to be even like that would be even more substantial different. So this is some plot in terms of the data coverage. That is scope one, total emission, scope 1, scope 2, and scope 3 emission. And so you see that like for ISS, it is always have a much larger coverage than Aiken and Aiken is Refinity and Bloomberg. What happened is that around 2018 and 19, I think that like ISS kind of increased their coverage, but then overall, what happened is that scope 3 emission is always smaller than the number of firms that actually disclose scope 1 and scope 2 emission, around 60% of the data point. So that is our first like finding. The second thing is in terms of like what we did, we chose like scatter plot a scatter plot that comparing scope emission between different data source. And so each of the panel is again total emission, scope 1, scope 2, and scope 3 emission. And so we want to see like what if between Refinity and ISS, what if between Bloomberg and ISS, and what if between like Refinity, Aiken, and Bloomberg. So essentially a three-way reconciliation. Ideally, what we want to see is that a straight line, meaning that whatever provider A report is also whatever provider B report. What we saw is not something similar, especially with like scope 2 and scope 3, scope 2 and scope 3 emission. There's a lot of diversion there, especially with like emission value of smaller firm. Scope 3 emission, there is a very interesting story behind. I think that it is mostly because ISS, they try to like correct scope 3 emission in the sense that there's so many inconsistency in reporting scope 3 emission, in the sense that like there's like 15 activity or 16 activity, I forgot already. So ISS try to like correct that. And so because of that, you see that the correlation between emission value among the three data provider is essentially very low for scope 3 emission. So here is what we, here is just like a table in which we summarize the diversion. So back to the scatter plot, the one that have dark blue value, meaning that they are very consistent within 1% error term, meaning that they are just like a rounding error instead of like a different in measurement. What we found is that like between like ISS and Refinity, ISS and Bloomberg, and Refinity and Bloomberg, only around like maximum is like around 70% of data point have identical data. But then like a large chunk of them is like within like, we say that acceptable measurement error within plus or minus 20%, even though like, even so, but then if we look at that from the carbon target perspective, we are trying to like, let's say reduce 7% every single year. This is going to be, this is going to create like inconsistency in data measurement. We look at the ranking. We was thinking, what if we like use the same data to rank the emission? And so what we found is that like most of the time, even though they have difference, if the firm is going to be in the same like design ranking or like in the upper ranking or lower ranking, meaning that maybe we have, we do have like diversion in carbon emission value. It will not affect ranking that much. So that is our finding in terms of the carbon footprint data. So that is the first part. The second part is actually in terms of prediction and forecasting emission. In our prior paper that we work with like Ivan and Juminda, what we want to do is that we want to develop a machine learning model to predict carbon emission for non-disclosing firm, meaning that like it is going to be, we use the disclosing firm to estimate the non-disclosing firm. And this is the approach that is similar to like Refinity, Aiken, Bloomberg. Recently, they also have a machine learning model. And just now in the morning, Andre also said that they have a regression-based model to predict carbon emission. For now, this paper will be a little bit different in the sense that we want to forecast emission. So meaning that like every single year, if they drop the earning core on yearly basis, we want to be able to forecast beforehand using financial data or like past emission data or past energy data, current energy data, whether we can actually forecast the carbon footprint. So that is the difference between this paper, this project and our other paper. What we found is that like for us to achieve the better prediction accuracies, it's always had to start with a historical model, meaning that like a prediction, the best prediction of one firm is always it passed. Meaning using if the firm already disclosed their past emission, they should use the historical model. And then if in case the firm already disclosed the energy consumption data, we should use that. And then in the case that there is no other better predictor, then we go with like purely financial data. What we found is actually that, what we found is actually that machine learning model, even though how fancy it is, it doesn't help improve a historical model. The reason why the historical model it doesn't work in here. So in here we have like the result of a historical model, the energy model, and a financial model. And we are looking at whole data only. And so what we found is that like historical model always achieve the best prediction accuracy, the lowest measurement error in terms of log strand form MAE. So in here what we see is that like even though how fancy machine learning model is, cannot beat a OS regression. And the reason why is when we have the lag emission in there, it is supposed to be a linear relationship. And so because of that, like the machine learning model, they are capturing the non-linearity, they are capturing skewness or whatever is it doesn't reflect in a historical model. Secondly, machine learning model can only help when we have no better past emission data, saying that if we use energy data and financial data, machine learning help here. And so what we found is that a OS regression, let's say in energy model, it had 0.55. In terms of the error term, it reduced to 0.44. So that is the machine learning model. And so like different from this paper compared to the paper that we have been working on, and even the paper that is conducted by Bloomberg, is in the sense that in our prior paper and even in Bloomberg paper, they choose gradient boosting trees as the best model. The thing with the tree-based model is that it is always bounded by the maximum value that you input in. So let's say that in the training data, we have like 1 million, a firm that have the maximum value of $1 million, 1 million ton in terms of CO2. The model is always bounded by that. So in the future, we have like 1.2 million ton of CO2, that model is going to fail. So that is the reason why instead of using that model, we use the linear forest tree model. So that is a combination between OS regression and random forest tree. So it is the best of both worlds. And in those cases, it improves the prediction accuracy. So I'm not going to talk more about that, but this is just to like showcase how the machine learning model is better than the other model. So this is the training set. And then in here, I'm plotting the OS regression in blue. Attributes, that is the tree-based model from Bloomberg or even from our prior paper, that is in yellow. And then the random forest, linear random forest is in green. And so what you see is that like actually the linear random forest to squeeze down the error range. It should be on the straight line. It is not on the straight line. However, it do squeeze down the error in the training set, the validation set, and the holdout set. And so that is sum up like our finding. Second finding is actually in terms of under forecasting. This morning, Andre mentioned about like that we have to be precaution in terms of like predicting carbon emission. And so what we figure out is that no matter what model you are using, even though it is OS regression, even though it is linear forestry model, this is always having some kind of like under predicting problem in here. And I'm not sure the reason why. I think that we need to figure out it better. But then one of the challenges of this modeling is that we have a very like small data set. We have very like bad predictor. And so because of that, whatever we try, we can only improve prediction accuracy to some certain degree. We cannot do better using this kind of like data. And so like with that, I'm going to like go into the detail, but then with that, like what Ben says is that it is not important how accurate our model are. It is important to understand the error distribution. And so because of that, and what we are going to do next, and Ben can talk about this much better than me, is that we are going to use a Monte Carlo simulation to understand like how does the error affect the result, like financial risk, carbon financial risk perplexity later on, or then that is our first thing. Second thing is that we want to model scope 3 emission, and for scope 3 emission, there are just like 15 different like activity. And we was thinking that maybe we cannot do it like individually, like scope 1 and scope 2, because we have data inconsistency. So we need to be able to model each activity within scope 3 emission. And so that is also another thing that we are thinking about. Last but not least, this one is have a machine learning model only help if we have a cross-sectional setting, in the sense that like you use this form to predict the other form. In the case we have a panel data in here, we have both time series problem and we both have like cross-sectional problem. So machine learning model like doesn't help in case that we have the historical model. And so that is, I think that is all for our result today. So yeah, with that we will